Okay, welcome everyone to the Oxford seminar. This week we'll be hearing from José, who'll be telling us about double functorial representation of index monoidal structures.
Thank you, Jason, for the invitation. And I will be talking about the work I've been doing in Topos for the past few months on this idea of representing certain semantics for logic called hyperdoctrines, more specifically regular hyperdoctrines, in terms of double functors between double categories. And as we'll see, this ends up having some connections to the theory of systems being developed in Topos. And there are some exciting potential new directions to go with this as well that I'll mention towards the end. So here's the plan. I will give you a reminder about classical hyperdoctrines, and I apologize if you're already quite familiar with these, but hopefully for the people who are not that acquainted with logic, this will be a nice and quick, albeit admittedly simple introduction to this. And then we will want to loosen up a little bit because there are too many restrictions with the classical notion that we might want to do without. So I'll mention a few ways you could extend this definition of classical hyperdoctrine in a way that turns out to be quite natural from the categorical point of view when we go to the double functors. And then we'll discuss the main result of this talk and the upcoming paper, which is this idea that this general notion of regular hyperdoctrine actually corresponds quite precisely to a certain type of double pseudofunctor between double categories. One direction of this is fairly conceptually neat. The other one will require quite a bit of pathing with compositors and so on, but I'll try to give you sort of a conceptual picture of what is going on. I will say something very briefly, most likely, about how this can be used to see logic as a system. This is actually work that's being done by David Jesmeyers that I hopefully will get to contribute to soon. And I'll end with some remarks for things to think about for the future. But as sort of an introduction, when you think about logic, right? You are in the situation where there are a few things you want to talk about, and you have some language that you use to talk about them. This is usually done, if you're familiar with just first-order logic, you have formulas which have variables, and you can combine different formulas by using logical connectives and using quantifiers, and that should correspond to semantic properties of your things. If you're saying that the formula exists X such that psi of xy is true, then that means that you should have some sort of witness. That's where the existential quantifier comes in, to the truth of phi of the witness and y, and so on. So here you have to be able to say how you do certain logical operations, like quantifying over elements, and also how to say, if I have a formula and I have a variable, how do I substitute that variable for some element of a structure, right? Some term, as we call it. So ultimately, logic is about explaining how you can define such operations. And one approach is that of given by hyperdoctrines. So the idea is you start with a category C. We sometimes call it the category of context, but the way you want to think about it is that this category has objects you want to talk about. And you could think conceptually that these objects have terms given of a certain type given by your object. So for example, C sets, you have some types which are the sets, and you might have some elements of type X for X is set. And the maps tell you how you transform something from one type to another. How do you transition between the types? And maybe for each type, you want to think of certain facts that might be true for elements of that type. So you associate some collection of predicates that things of that type may or may not satisfy. But then you need to explain how you do logical operations, and those logical operations should be compatible with how you transform terms of one type into terms of another type. So you should be able to describe the following things. First of all, if I have some predicate, some formula about things of type Y, and I have a way of transforming something of type X into something of type Y, that should give you something you can say about things of type X. So if you have a formula phi of Y, and you have a map from X to Y, you now have a formula phi of f of X that is something about things of type X. So you should be able to describe how you do this substitution, and it should be compatible with how you transform things of type X with things of type Y. And you should also be able to explain how you can combine basic facts to make more complicated facts, right? So that corresponds to applying logical connectives like ands and ors and maybe implications and things like that. And also how you perform quantification. Levier's insight here is that actually, if you know how to describe how you make substitutions, then you can describe quantification by saying that the substitution operation has adjoints. That was Levier's big insight, and that's what led us to this definition. So let's talk about the most basic notion. What is a regular hyperdoctrine? A regular hyperdoctrine is the description of all the things I just mentioned. I have my category C of contexts. Here we assume that it has finite products, let's say finite limits to make it simpler, because we might need some pullbacks. And it takes values in posets. So the way you should read this is for each object X in C, I associate a partially ordered set of predicates, and the partial order is deduction. From fact A, I can deduce fact B. Okay, that's how we are ordering that. But as I said, we should be able to combine basic facts using logical connectives. So in fact, each Px is not just a poset, but it's a poset equipped with a Cartesian monoidal structure. It's what's called a Meetsand lattice. So here we can't do all the logical connectives, but we can do and we have a top element that serves as truth, because everything implies truth, right? So generally speaking, if you wanted to deal with more complicated logics, Px would be a model for some stronger kind of algebraic logic. Could be Boolean algebras if you want to have classical logic, could be Heyting algebras for intuitionist first order logic and so on. And okay, that deals with the logical connectives. Now, for each way of transforming something of type X into something of type Y, I have this functor Pf that transforms a predicate of, given a predicate of type Y, so a predicate about things in Y, gives me a predicate about things in X. This is describing the substitution operation, how you actually perform this substitution. And the fact that this is a functor means it preserves the implication operation in your logic, right? The deduction operation. And here we assume it has a left adjoint, which will play the role of existential quantification. We'll see when we talk about a simple example how exactly that recovers classical sort of quantification. But this data is subject to a few more restrictions. First of all, the adjoint satisfy the Beck-Chevalley condition. If I have a pullback square in the category of contexts, then one thing I can do is apply the functor p to that square. And of course, it will give me a new commutative square. And then I can stick some units and co-units to the side of that square, and that will give me a canonical map comparing a combination. So it will be from PG, so exists H composed with pk to pg composed with exist f. And we ask that this canonical map is invertible. I'll call those inverses Beck-Chevalley cells, okay? And we have a very similar story that we call the Frobenius reciprocity property. For each f from x to y, I can also build a canonical map that goes from exists f, pf and identity to identity and exists f. The way you build this map is, of course, if pf is a monoidal functor, I should probably have. Yeah, no, it's fine because it's a right adjoint. So here pf is automatically preserving limits because it's a right adjoint. So it preserves the AND operation. That makes it strong monoidal. Its left adjoint exists f is comonoidal. So at the bottom, if you look at exists f, pf, and identity px, well, exists f takes this conjunction to exist f, pf, and exist f, and you can just add the co-unit and exist f to get to the other side. And now we're saying this canonical map is inverted. All right. Now, what do these things actually say on the logical side? There is a very instructive example that will help us see. So let's talk about the most basic example. Your contexts are sets, and P is power set. So my predicates are subsets of X. And if you believe in set theory, subsets of X are the same as predicates about X, right? We can form the subset of all the things that satisfy the formula. So you can think, interchangeably about formulas in the language of set theory, so usual maps, and subsets of X. And of course, if I look at predicates about the terminal object one, well, we have two subsets, empty set and the whole thing. Those play the role of the truth values, true and false. If I have a map F, well, substitution behaves in the exact way that you expect. It takes the predicate phi of y, or the subset defined by a predicate phi of y, to the predicate defined by phi of f of x. So this is inverse image. And this has a left adjoint, which just takes the image of the subset under f. So existential quantification, when you write down what that actually says, you can see where the classical quantification shows up. It takes the set of all the x's that's phi of x to the set of all the y's for which there is an x, such that y is a f of x and phi is true of x. Now let's look at a particular case. Let's say that my map F is a projection. Okay, so I have my projection from x times y to y. And I do this existential quantification along the projection. Well, saying there is an xy such that y is the projection of that pair and something's true, it's just saying there is an x such that phi of xy. So you have the usual quantification over a variable. If you want to quantify over a variable, you take the projection that makes it disappear and quantify over that. Now, what do Beck-Chevalley and Frobenius say in this context? Well, Beck-Chevalley is saying that you can. Sorry, we have. I turn on the lights again. Cool. Beck-Chevalley is saying that existential quantification and substitution commute whenever that makes sense. So if I have some phi of xy, I might want to replace the y with some term t and then quantify over x. Or I might want to take the formula exists x phi of xy and then replace the y with t, and the results are the same. So that's what Beck-Chevalley is saying. And Frobenius is saying that if I have some formula some formula phi and some variable that is not free, then saying that exists an X such that phi of y and some psi of xy is the same thing as saying that phi of y and I have a witness to psi of xy. So I can take phi of anything that doesn't depend on X out of the quantifier. Makes sense. Right, so this is sort of the basic example, and it's sort of good to see how things look in very traditional logic terms. But of course, we have this more general notion of substitution and quantification. Let's look at one more example just to fully get the classical picture in this framework. Let's say T is a regular theory. What does that mean? It's a logical theory whose axioms only use and true relations and existential quantification. So this could be something like the theory of graphs or whatever. Then out of it, I can build a hyperdoctrine. So how do I do that? C is what's called its syntactic category. I won't get into details of what that is, but objects are essentially lists of variables of certain types. And to each context, we can build what's called the Lindenbaum-Tarski algebra for the theory T with variables in that context. How this construction works, so if you'd have some formulas on variables x, y, z, for example, you could consider all the formulas and then consider that set quotiented out by the equivalence relation saying that two formulas are the same if the theory believes they're the same. Here, one important thing, saying that the theory believes they're the same means I can prove out of the axioms of the theory in the fragment of logic that only uses and true existential quantification that those things are equivalent. This thing is automatically a meet semilattice with the obvious operations. So end of an equivalence class is the equivalence class of the ends and so on. And that's how you do this construction. If T is the empty theory, this is a way of constructing the free meet semilattice on a set of propositions. Okay. So that's how you get the predicates over each possible context. And that lets you see the theory as a hyperdoctrine. Okay. Now, this can be a bit too restrictive. So let me tell you a few ways you might want to loosen up this definition of hyperdoctrine. First, there is no reason why my predicates should be elements of a poset. Maybe you want something a little broader than that. Maybe you're reasoning your predicates as objects in a category. This would be the case, for example, if you wanted the type theory rather than just logic, right? There is no reason why you should have an AND operation that is defined by the Cartesian monoidal structure. So like maybe you still want it to be fruit of some universal property, but there is no reason why this universal property should be that of a product. So maybe you want to replace n with some tensor product of some kind. And also, maybe you don't need to be able to take like existential quantifiers over any map. Maybe you just want a few of them. I can imagine that maybe geometers might see certain cases where that's true. So let's try and introduce fixes to all of these things. So one way you can do this is saying, well, maybe I don't have all the pullbacks, I only have certain pullbacks. And there is this notion of an adequate triple that captures exactly what you need in order for you to have pullbacks that result in a span construction, which will be important later. So here C is some category with finite limits. L and R are classes of maps in C, closed under, they have all the identities and closed under composition. And you can take pullbacks of things in L along things in R, plus some stability properties. We're also saying this adequate triple is Cartesian. So for the purposes of this talk, what that means is, in practice, I'm taking R to be all maps because we always have PF, right? And L is closed under products. Okay. And so that deals with the fact that you only have some quantifiers, because now you will only be able to take existential quantification along things in L, not in general, just things in L. The predicates will form a monoid, a pseudomonoid, in some Cartesian category. So that means your predicates don't form just a meet semilattice, but they are some object in some category, and there is a tensor product defined on that we can use that plays the role of AND. And we can go back to this definition and relax all these things accordingly to get the notion of what I call a CLR regular monoidal structure. So here, it's no longer a functor, it's a pseudofunctor. We don't have pos anymore, we have a two-category K, a Cartesian two-category K. Each poset is not a meet semilattice, it's a pseudomonoid in K. The functors, it's not just that the functors have a left adjoint, the pseudofunctor is strong monoidal and has a left adjoint. So each PF is strong monoidal and has a left adjoint. And these adjoints satisfy Beck-Chevalley and Frobenius, but this time it's only Beck-Chevalley for pullbacks in the adequate triple, and Frobenius holds for the tensor product, not AND. So it exists F PF tensor identity to identity tensor exists there. Okay. I might have to speed up a little bit. So let's see some examples of where we might want to have this level of generality. So for starters, if C has finite limits, I can define a pseudofunctor from C up into symmetric monoidal categories and strong monoidal functors by taking X to the slice of C over X. Since C has pullbacks, these slices all have products, so they're Cartesian monoidal, and these are our fibers, and each PF will be just pulling back along F. All of them have left adjoints, which we call dependent sums, and the fact that they satisfy Beck-Chevalley and Frobenius is precisely the pullback pasting lemma. Okay?
I have a question. So I think there's a sort of subtle point where before you defined, you said that P was strong monoidal.
PF.
PF was strong monoidal, but that, did you express it as a consequence of the fact that P itself is monoidal?
We'll talk about that later.
Okay, but so we should think of P as going into symmetric monoids in some.
In cache.
Right, and the morphisms go just fine. Okay.
Yeah. Okay, another example. This time we want a more interesting AND. So let's define for each set A the set of functions from A to 0 infinity, including. And this thing is a monoidal poset with tensor product given by addition, and the ordering is greater or equal. If I have a map from A to B, I can precompose with F to get a map from PB to PA, and this is strict monoidal, preserves addition. And the assignment is functorial. You can build a left adjoint for this by taking some infima. It's the map that takes a function from A to 0 infinity to the function from B to 0 infinity, mapping a B to the infimum over all the A's that map to B of 5A. And you can just check that this does satisfy Beck-Chevalley and Frobenius. So this is kind of like a metric sort of logic where your predicates are actually measuring something, some real number. Okay. Now, what is the theorem? The theorem is, if I have a Cartesian adequate triple and a Cartesian two category, then the two things are the same. A regular index monoidal structure in K and a Lex symmetric monoidal double pseudofunctor from span up over the adequate triple and quintet of K. So just a reminder, quintet of K is a double category with tight and loose maps given by just the maps in K, and the squares are just the cells in K.
And span has like left legs in L, right legs in R.
Exactly. And the monoidal laxiter for these functors P dot are what we call companion commuter cells. I'll give a definition later, just to recap what that is, but for our purposes, that means that if you look at the cell given by mu on one morphisms, that is invertible.
And op, yeah, means like tight op, right?
Sorry, I mean on spans. So mu on spans is invertible.
Sure, but the domain of P bullet is like that op means that's
The up means you're upping the tight direction, not the loose. Okay. Now, let's discuss how you can actually take a regular index monoidal structure and turn that into a double pseudofunctor. So let's fix such a thing. First observation, each of the PFs is a strong monoidal map. So the left adjoint, which I guess is the other way around in the slide for some reason, the left adjoint also is a pseudofunctor with a structure that you get by taking mates of the structures of things for PF. And one very interesting observation that relates to, I guess, what Jason was talking about. You can move the monoidal structure from the fibers to P itself. We'll see in a bit how that looks in practice. But the idea is all the fibers, all the P axes are pseudomonoids, and you can move all that monoidal structure to P itself. So you can think of this as being just a pseudofunctor from C up to K that is like symmetric monoidal with the Cartesian structures. So that's the first step.
Sorry, you said the exists F are also pseudofunctors. What does that mean in that context?
From C up to K.
Oh, okay, but right, the functor which sends, but it's not like each exists F as a pseudofunctor in.
Oh, sorry, my bad. No, that's each exists F is comonoidal.
Right, and you get a pseudofunctor from C into right. Okay.
From this second bullet point. Okay, so here's the idea. We have this P from C up to K, which is Cartesian monoidal, and we extend it to a double functor, a double pseudofunctor. So a double pseudofunctor has both its tight and loose components pseudo, hence the name. Okay, so I'm saying that the tight component of this P dot is just P, and the loose component goes like this. It maps a span with x2 in L to this pull push, exists x2 PF x1, and it maps a square to this thing. So the string diagrams here go from bottom to top, and they are in diagrammatic order. So here, what we have on the bottom is exist x2, px1, pf1, and that goes to pf2, exists y2, py1. So that's actually from P dot of X as a span, composed with PF1 to PF2, P dot of Y as a span. So when I have the merging lines, that is a compositor, and the splitting lines is the inverse of the compositor for our pseudofunctor, and we have that for P. And the unit and co-unit there, the upper index is telling you which adjunction it comes from. So eta y2 is the unit for exists y2 left adjoint to P of y2. So this thing gives you the action of P dot on squares.
So this is a 2 cell in K to be thought of as a square in quintet.
Indeed,
Okay.
exactly. Okay, now P dot on spans should be pseudo. So how does the loose compositor look like? So if I have a composite of spans like that, how do I map P dot of the composite to the composite of the P dots? With this pretty little string diagram. So this is using both the structure of the exists and the P's. So the compositors for P and exist to make this work. At the bottom, you have P dot of the compositors. Sorry, P dot of the composite. On the top, you have the composite of the P dots. Now,
Sorry, one sec. So that's like giving like the laxatives for like a monoidal structure.
yeah,
Is it right? And the point is these are invertible.
yes.
Is that
So this thing,
mhm.
the P dot blank. So these are the components of P dot circle at XX prime.
Mhm.
P dot circle is a pseudo-natural transformation. And the inverse to this thing
Mhm.
is given by this, where the cell you have on the bottom is the Beck-Chevalley cell. So you need Beck-Chevalley in order for this to be pseudo-natural. Okay. I did not bother to write string diagrams for this.
Good.
It's good to have a mix, right?
This is way more readable.
If you think so. All right. What about uniter? Again, you just put together the structures of P and exists. The structure of exists is essentially coming from the structure of P, so nothing too exciting here. And the Beck-Chevalley property was used, as I mentioned, to ensure pseudo-naturality of these loose compositors. What about Frobenius? Well, Frobenius has to do with the monoidal structure. We'll see in a bit how. But first, let me say something about this monoidal structure. So I had quoted this theorem saying that you can move the monoidal structure from the fibers to P, but how exactly does that work? Well, if I have the monoidal structure on the fibers, I define the monoidal laxative for P as a functor from C up to K, a pseudofunctor, in this way. So first I multiply P of the projections to go from Px times Py to P of x times y times P of x times y. And now I can use the tensor product in P of x, y. And in a similar way, you get a monoidal unit induced by the units of the pseudomonoids. And now we want to say that I can extend this monoidal structure from P to P dot as a double functor. So I had the monoidal structure on P as a pseudofunctor, and that will extend to a monoidal structure on P dot as a double pseudofunctor. As we know that P dot on tights is just P, we should just define mu dot, the extension to P dot, should just be mu on the tight component, and we want to define what it should be on the loose component. So let's show first, mention that mu extends to a tight pseudo transformation. So what does it do to spans? This is the definition of mu dot on spans. So here A and X are spans, A is made by A1 and A2, and X is made by X1 and X2. And what you do here is you look at mu, which was the Laxter for P. And since P is a monoidal pseudofunctor, this is a pseudo-natural transformation. So this mu, basically the naturality square for mu, is invertible. We start with that, and then we take the mate of the naturality square for the second bit of the span. And that's how we form this. So the thing on the top is just the mate of mu A2, X2. Okay, so this thing is a tight pseudo transformation, and in fact, it makes the loose component of P dot monoidal. Here's how it works. Since P is monoidal, I have cells that serve as witness to the truth of the monoidal associativity axiom. And these things are invertible cells. So instead of just saying I have a commutative diagram, I'm just saying this thing is an invertible cell. And the way this invertible cell relates to the naturality squares for mu is this, by the fact that P is monoidal. And using these relations, you can show that P dot, well, mu dot satisfies the dual equation, so it's comonoidal. So this is just putting together the fact that P is monoidal and exists as comonoidal, and using these relations for both P and exists, and doing some computations with string diagrams to check this. All right. Similarly, you can do basically the same process to show that you have the unit laws and symmetry axioms for mu dot, but this time as, sorry, for P dot as a double pseudofunctor. Now, there is this added bit in the theorem about commuter companions. So what is that? So if I have a square like this in a double category, we say it's a companion commuter if when I stick companions to the type maps on both sides, the result is invertible. It's a globular tight isomorphism. Okay. Of course, if we are in quintet, these companion cells, the little squares on the sides, are not very interesting. They're just identities. So actually, alpha being a companion commuter in quintet just means it's an invertible cell in K. So for us, the fact that this is a companion commuter is just saying, oh, it's invertible in K, so it's not super interesting, but it will play a role in the observations that come later. Position, that's where Frobenius comes in. Frobenius implies that all of the mu dots of spans are companion commuter cells. So here's the idea. We saw that mu dot on spans is built from the mu's like this, right? So we have some mu inverse, and then we have the mate of another mu. The mu itself, like each mu A1, X1 is invertible. So if I want to show mu dot is invertible, I just need the top bit to be invertible, the mate of mu A2, X2. But
sorry, which bit to be? Oh, okay, sorry. Yeah, I see.
The mate of mu A2, X2 needs to be invertible.
Because the unit and...
So here's the thing. We already know the bit on the bottom is invertible.
Yeah.
So if we can show the bit on the top, which is, you know, everything except for the square on the bottom.
Including the unit and co-unit.
Yeah, including the unit.
All right, which is by definition the mate of mu.
Indeed.
Okay, sorry. Yes.
We want to show that is invertible. But the mate of an invertible cell, even an identity cell, doesn't have to be invertible. So, you know, you need something extra to be able to show this is true. And as it turns out, you can construct this inverse from the Beck-Chevalley and Frobenius cells. And this is what it looks like. I will not subject you to a bunch of calculations to show that this works, but it's actually conceptually not that complicated. All we're doing is splitting it up in a sort of trivial composition. So we're writing exists x2 times y2 as identity times exists identity times y2, and exists x2 times identity. We're doing this split and then undoing the split later, but you get to do this because you have these cells. And if you just use the definition of what B's and F's, so the Frobenius and Beck-Chevalley cells are inverse true, you get precisely the mate of mu x2 y2. But it's quite a bit of work to get these calculations done. And nearly impossible without string diagrams, I should say, or at least in a sensible way. So putting everything together, a CLR regular index monoidal structure can be extended to a Lex-symmetric monoidal double pseudofunctor from span up to quintet, whose Lexters are companion quintes. What about the Converse?
Can you remind us what exactly? So there was this thing about the the loose laxatives being like co-monoidal or something. Is that just like part of what a sensible definition for a symmetric monoidal double pseudofunctors of that form is?
Yeah, the nuisance with the op thing is because we're looking at span op, and span op only ops the tight direction of the loose direction.
Would some of this go away? Like we start off by looking at lax monoidal functors out of C op, which are the same as like co-lax monoidal functors out of co-Cartesian C.
Yeah.
And then the op presumably disappears from here and it's co-span or something, doesn't it?
I think what happens is this slightly annoying thing that what does it mean for a pseudofunctor to be lax monoidal? Because the pseudofunctor is from C op, but C is the thing that is actually Cartesian monoidal, not C op. C op is co-Cartesian.
Right.
So there is a bit of weird terminology going on in some of the literature where this thing should morally be co-monoidal into K op, but it's being called monoidal.
Right, okay. Oh, right, I see.
Yeah.
Okay.
So it's slightly, yeah. But I think here it's essentially because the tight bit is being opt, but the loose bit's not. But really it should be, I guess, called lax symmetric comonoidal, but anyway.
Right, okay.
If we did geometry instead of logic, the op would go away.
But at what cost? Okay, for the converse, can we all agree that having to deal with all these coherence things and needing the string diagrams and so on is too much? So I did it in one direction in that full detail because that's the direction where the examples come from, and they are loose in that sense in the examples. But for the converse, there is no reason to do this, and I'll happily just assume this strictification theorem proved by Grandis and Perret that basically let you go from double pseudofunctor to just double functor. So let's just pretend that that was the case. So we're looking at a symmetric monoidal double functor, and whose Lexters are companion commuters, and we'll try to get an index monoidal structure that is just functorial instead of pseudofunctorial.
Sorry, so symmetric monoidal double functor, is that still pseudo in some? Lexter is referring to the monoidal structure?
Yeah, so it's like symmetric monoidal, so the monoidal structure is still like symmetric. When you say double pseudofunctor, the tight and loose are both pseudo. If you're saying a pseudo double functor, only the loose one is pseudo, but we are strictifying everything is true.
How do we strictify
Except the
span? Like what's the composition in?
We're not strictifying span, we're strictifying the functor.
Okay. Is that like a sense of, so that I guess the thing is span is sort of like a pseudo double category, and we're looking at like a strict double functor out of it.
Yes.
Okay.
Okay, so that lets us get rid of a lot of nonsense, and I think it will be a bit more conceptually clear and quicker from now on. So we fixed a Lax-symmetric monoidal double functor from span off to quintet, and we're supposing the Laxters are companion commuters. So the mu's on spans are all invertible cells. Step one, we note that a normal double functor, so it preserves like the uniters are invertible. They preserve companions and conjoints. Now, if I take a tight map in spans, it always has a companion and a conjoint. And then if I apply a functor, a double functor that preserves companions and conjoints, they become companions and conjoints in quintet.
How does the companions and conjoints relate to the adequate triple structure? Like wait. So I'm trying to put this together. So okay, so F, this is arbitrary F, it's not necessarily one inside L or
F here is tight, so F should be in R.
F is in R. Okay.
Yeah.
And are the companions and conjoints also both in?
The conjoint will be in, well, the image of the conjoint will be in L.
Okay. 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 Okay.
No, but that's a good point. So we have companions and conjoints, and they get mapped to companions and conjoints. So if I have F shriek as the conjoint of F, their image under Q will be conjoints in quintet, but that's just an adjunction internal to K. So we get some Q F shriek left adjoint to QF. Again, they're inverted in this slide because I keep forgetting if it's /v dash or dash v. Right, so that's how you get your adjoints. So your existential quantification here is Q of F shriek, and QF is QF. So that's first step. Step two, Beck-Chevalley essentially just comes from the fact that pullbacks are just composites in span, loose composites, and you can write a loose composite in two ways. So if you look here, G shriek composed with K upper star as loose maps just gives you the span HF again, because you have this pullback. But you can also write the span HF as 8 star loose composite F shriek. So you have this iso between these two ways of doing this composite, and Q preserves that. And when you look at what the image under Q is, you get Beck-Chevalley. There is a little bit more detail here because the Beck-Chevalley is not just saying these things are isomorphic, but that the isomorphism is inverse to a specific thing, but it's true. Okay. So that's how you get Beck-Chevalley. It's just an artifact of the way loose composes in span and the fact that your Q is defined in span and preserves these things. Step 3, let's get a monoidal structure on the fibers. Well, Q has a monoidal structure, and we can do essentially the backwards procedure from before and get a monoidal structure on the fibers in this way. First, you go from QA times QA to Q of A times A by using the Laxter for Q, and then you apply Q of the diagonal. And you get monoidal units as well. So doing this infuses each of the QAs with the structure of the pseudomonoid. Well, here just the monoid. And step 4 is how you get Frobenius. And again, Frobenius is related to those companion commuters. So how does this work? So I have my mu. I should have written mu dot. I have my mu dot. I guess I'm calling it mu because it's no longer a dot of something, but yeah. I have my mu, which is the symmetric monoidal double. It's the double functorial Laxter. And here I have this I'm calling LA just the loose identities, okay? Loose identity on A is LA. So I have a map from here to here, which is just the component of the double extra at F star and the identity goes from here to here. And you can fill out the rest of this square. Here you have a Beck-Chevalley square. And here on the bottom, you have the inverse of the companion commuter thing, which you're assuming exists. And this thing, this whole thing here, this composite, is inverse to the canonical Frobenius cell that we need to exist. So that's where having your companion commuter gives you Frobenius. So you get the full theorem saying those two kinds of things are equivalent. Okay. Now, how does this relate? I have 5 minutes. How does this relate to systems? I won't go into any detail on this because you can check what David Jess wrote in the forest on this, and it's his stuff anyway. But we started with P and we turned P dot into this like symmetric monoidal double pseudofunctor thing. And through some sorcery, essentially, you can actually do this pullback and still land in like symmetric monoidal double pseudofunctors. And that defines this thing that is called search P. We can ignore the co-op because, of course, that uniquely defines what the search P is. And that serves as interface for a system. So that's the symmetric monoidal double category of interfaces for a certain system. I didn't write it down, but what does it look like? So what does this symmetric monoidal double category look like? So its objects are pairs, where X is something in C, and the second component of the pair is a predicate over X. So it's something in PX. Maps, tight morphisms, basically give you ways of comparing a predicate over X and a predicate over Y if you have a map from X to Y. So it's like a map from the predicate over X to the substitution of the predicate over Y over some map F. You also get things on the loose side that basically lets you have over a span, you have a span of predicates and a comparison map between those. And you can also define something for squares. But essentially what this is saying is it's giving you a way of defining what it means for you to have something and the certificate attached to it, which is in the logic PX, the logic P. And since this is just a system, you can use it to compose other systems. Now, some final observations with our few minutes. So some further directions. I'm always on the lookout for more examples of these things. I need to talk to Owen about creedal relations, because he says there's something there. I need to talk to Tim about potential examples in geometry.
I think, yeah, just like my one small comment, or it's only 2 minutes, is that I think modulo an issue with op, which I think is a logic geometry op. The conditions you put on are like 80% overlap with the conditions of what's called a Grothendieck pseudofunctor in geometry. And like the key example here is you would take C, I'm going to get an op wrong, but you would take C to be affine schemes, and you would take P to be the thing that sends an affine scheme to its like symmetric monoidal category of quasi-coherent sheaves on that scheme. Then Frobenius reciprocity is what's called the projection formula. Beck-Chevalley holds by definition. This is precise. It's a really cool example. There's a lot of cool stuff. And I think this certification thing looks a lot like, essentially like the lens construction for ring spaces or something. Like it's very, I think there's a cool geometry example, is the short story. I'd love to talk about this.
Then we should talk about this in more detail.
Yeah.
Another thing. Another obvious direction, we had some sort of bare minimum structure on the fibers, right? It's just a pseudomonoid, but you could have more stuff. You could have some modalities in there. You could have you know, a right adjoint to the tensor product. So what happens if the fibers are monoidal closed? That would be good because we would have access to more expressive logics. So for first order logic, for example, the hygiene implication. So the implication operation is of course right adjoint to and. So that would be one of those things. And if you want dependent products as well, that's the kind of situation. So you might want to look at cases where the fibers are monoidal closed and try to, you know, transfer it to the whole of P and yada yada. It's something that Schumann has sort of worked out, but it's not as straightforward as the previous stuff. There is more work that needs to be done. Now, what I think is more interesting for the future, we saw that Beck-Chevalley is fruit of your double functor being defined on span. And Frobenius is because you have Beck-Chevalley and the monoidal Lexter is a companion commuter. But there is no reason for any of this to be true for your target to be a quintet double category, right? You just need to have enough companions and conjoints so that it makes sense to say the Lexter is a companion commuter, and that, you know, you have conjoints in the target to become your existential quantifier and your substitution. So in principle, you could do this with something else like profunctors or something like that. And actually, that tells you that there is a more general notion of hyperdoctrine being there, just saying a hyperdoctrine is a lax monoidal pseudo double functor between double categories. And I guess you want enough companions and conjoints on these things. This has a very nice consequence, which is Beck-Chevalley is about pullbacks, but maybe you don't want it to be defined in terms of, you know, a universal property like pullback. Maybe you want it to be defined, like you might want a more general version of Beck-Chevalley, which, you know, Beck-Chevalley has the pullbacks because pullbacks are how you do loose composites and spans. But maybe there is a story about if your domain of your double functor is some other double category, and you can do a loose composite in two different ways, then a Beck-Chevalley condition would be just saying your functor preserves those. So, yeah.
There's this like you've got like rather than pullback squares, some other notion of distinguished squares, which allows you to define composite. Okay, and those have the back. Okay.
And that leads us to the final observation. In a sense, these double functors we just constructed that emerge from hyperdoctrines are in a sense trivial. And the reason why is because the loose component is fully determined by the tight component, right? We build the loose component as composing exists with P, but exists and all of the structure of exists just comes from the structure of P by taking mates. So in a sense, everything is being determined by the tight component, and that's why our P dot is just an extension of P, and the monoidal structure is just an extension from the one we had, and so on. But perhaps there are more interesting examples where, you know, you don't have quintet and span necessarily that fit into this, where the tight and loose components contribute to the logic sort of independently or, you know, in equal measure. So that would be interesting to see. So maybe the loose component could have more of an impact on the logic. So right on time, that's it. That's all I have for today. Thank you for listening.
Okay, that's all. Thank you, José, for his talk. Okay, questions. I mean, there's a lot of like technical details I'd like to maybe like understand
Absolutely.
for myself, but I guess so. The thing you were saying at the end about like the loose direction being determined by the tight direction, I guess is that like, can I view that as a consequence of the fact that in span all the looses are composites of companions and conjoints of tights? Is that
I think there is more to it than that, because if you go back all the way, let's see. The problem is also in the way you define the functor, right? So like, where is that? Yeah. So here, your P is defined on the loose components as the composite of xx2 and px1.
Mm.
And the xx2 is determined by the px2.
But so is this like,
And this also goes for the, the further structure, like the compositors and the monoidal structure and so on.
But are you not forced into this, like, exists x2, this push-pull thing is like, the point is exists x2 is like the conjoint of like the tight map and span x2 and span up or something, and P is the companion. Are you not forced, like does your double pseudofunctor not like necessarily need to preserve conjoints and companions? In which case would this not like be forced to? I guess the point is x1, x2, that's like the composite of the, I might be getting this wrong way around, but like the conjoint of the vertical map x1 and the companion of the map in R. I'm gonna get L and R and conjoint and companion mixed up.
Sure.
But like every span is built out of conjoints and companions, so things in L and R.
Yeah.
And does that not say that like the image of your loose must be sent to the conjoint companion of the typed arrow?
I think the point I was making further ahead is that you don't need to be starting with span, right?
Oh, right. But like, is the issue with span that it has this property that all the looses are composites of companions and conjoints, and if you click like
I suppose. There is also the fact that you're landing in quintet. If you are landing somewhere else, maybe there is more that could be happening there. But, yeah. But that is a good point.
Right. And the point about saying like your codomain category has enough companions and commuters.
Conjoints.
Oh, sorry, yeah. Has enough companions and conjoints. Well, but is it not the case that all the companions and the conjoints should come from, that would be true if like all the appropriate types of companions and conjoints, and what's the
So the thing is, we're getting our existential quantification out of the conjoints. If your target is such that only very trivial things have conjoints, then your logic will be trivial, right?
Right.
That's what I mean by having enough conjoints.
Right, but do you not have to like map a conjoint type to a conjoint?
If your double functor is normal, yes.
Right, okay, right, I see that identity one looses and types that are relevant to that definition. Okay. Right, and that section was all in the bit where we're assuming we've got a strict double functor, so that. Okay. Okay, I did have another like general question. When are there many like interesting examples where using the adequate triple verb? So by the way, so for span CLR, I think maybe Tim asked about this and I wasn't paying attention, but the point is you got your left, your spans, one leg is an L, one leg is an R, and like everything in L will be those one cells which are conjoints or something, or and the other set companions.
So all the stuff in L has existential quantification. That's the idea.
Okay.
So like you have the right class R. If you look at the situation here where you have P from C up to K, PF has to be defined for every F in C. Because P is a functor. So that means you kind of have to take the right class to be the whole of C. So like all the maps in C. That's the right class.
PF is defined for every map. Sorry, why do you have to take the R to be the entire right?
Because
Oh,
PF is defined for OF.
right. Okay, if you're going into quintet or something, then I guess the point is every morphism in quintet has a companion.
Yeah.
And
Which is just itself
okay.
as a mapping K. But my point here, if you look at this P, right? P from C object K. PF is defined for every F in C. So, you know, I have to have all the Fs in C in the right class.
Yeah.
The question is, what is in the left class? And the left class will be more restricted
Okay.
in general.
I mean, you not like, I mean, clearly P of F needs to be defined for every F and R, and it also needs to be defined for every F. Does that say that R has to be like every F? Does that question make sense? Like, why does R need to be, clearly everything in R needs to have PF defined for it, but does that mean that R needs to be all the Fs for which PF is defined, or?
I mean, that's what happens in the examples so far. That's actually something that will probably pop up when I speak to Tim in detail about the geometry examples, because I think those are the settings where the adequate triple stuff is more relevant, and where you might have like more restricted classes where you have your adjoints. So I'm kind of interested to see this, because the examples we have so far are sort of trivial on the adequate triple side of things. All the adequate triples in the examples, right, that we looked before were just like all maps, like L and R, just all maps, right? But it would be interesting to see some cases where that isn't the case.
Okay, are there any other questions? If not, let's thank Jose again for his talk.